find this particular equation, what do we have? We have the quadratic expression R1 squared minus 0.6 R1 minus 1.95 equals to 0. So that we can solve this quadratic equation for R1. And that gives us this. R1 equals 0.6 plus or minus square root of 4.6 squared minus 4 brackets minus 1.95, all divided by 2. So solving that carefully, we have R1 equals 0.6 plus or minus 2.87 over 2. R1 is equal to 1.74 ohms. That's a positive value. The negative value is not accounted for. We don't need it. So we only stick to the positive value. Therefore, R2 is equal to 1.95 minus R1. That is 1.95 minus 1.74. It gives us 0.21. R2 equals 0.21. And then small r is equal to R1 plus 6.55. That is R equals 1.74 plus 6.55. That is using the previous equations, the three equations we have before. So that R equals 1.75 plus 6.55. So R equals 8.29 ohms. 8.29 ohms. Now the formula goes to say distance from testing end is equal to R2 divided by resistance per meter length. Resistance per meter length, therefore, equals R2 over distance from testing end. So if you solve that, now we have resistance per meter length is equal to 0.22 divided by 270.14. That is equal to 0.000821 ohm. Therefore, resistance per meter length equals total cable resistance divided by length of cable. Therefore, length of cable is equal to total cable resistance divided by resistance per meter length. Total cable resistance is 1.95 ohms. And so length of cable is equal to 1.95 ohm divided by 0.000 divided by 1.95 divided by 0.000821. And the answer is 2375.91 meters. And that is the solution. That is the solution for problem number 1. Now, problem number 2. With the aid of a diagram, explain and derive necessary equations for the Murray-Loop test of locating earth faults in cables. So we have the solution as follows. Sir. Sorry. So we have solution. Murray-Loop test is a method for locating earth faults or short-circuit faults in underground cables. The method is a modification of Wheatstone bridge, as we know. In this case, we replace the 2 arms of the Wheatstone bridge by the course of 40 cable, as we show in this diagram. You can see the sand cable, that is capital L, sand core, and the 40 cable down here. So they both are joined together with a low resistance link. So the bridge is balanced by setting resistances P and Q, variable resistances. Okay, so at balance, the position of the fault from the test end of the cable is given by using when we use the relation that R is proportional to the length. So we can use the resistance in place of length, or length in place of resistance. So we can have Q over P equals L, that is sand core, plus L minus D, that's the remaining portion here, all right? That's 1 arm of the bridge now, divided by D. This is the small letter D here. The distance from the testing point to the 40, to the fault location. So we have Q over P equals 2L minus D over D. Therefore, QD equals 2LP minus PD. All right. Okay. So when we solve that out, we have QD equals 2LP minus PD. QD plus PD is equal to 2LP. D equals 2LP over P plus Q. That is 2LP over P plus Q. And that is the relation. That's the relationship you can use to get the value of the distance from testing end. Model loop tests are primarily used for locating force on low resistance cable conductors. The greater accuracy can be achieved if the test is repeated at one end, other end, at the other end of the cable, and the main position of distance D is taken as the point fault. So that's what we have, and that's the solution to that problem. So if you write out this, you possibly get the full marks. Full marks. That's about 7 marks. About 7 marks. All right. Now the last problem, number 3. The last tutorial problem, a resistive temperature measuring metallic elements made from tungsten wire has a 14 ohm resistance at 20 degrees C. When the temperature of the measured quantity is raised to 120 degrees C, calculate the resistance of the resistive element if the temperature coefficient of resistance for tungsten metal is 0.005 per degree C. Now we have the solution as follows. The formula of interest is right here. R at a particular temperature equals R reference multiplied by brackets 1 plus alpha delta T, where alpha is the temperature coefficient of resistance. So R reference here is the temperature at reference point, that is at 20 degrees C, and that is 14 ohms. And alpha is given as 0.005 per degree C. So change in temperature will be the difference between 120 to 20 degrees C. So we can substitute those into the formula. We have 14 bracket 1 plus 0.005 multiplied by 100 degrees C. The answer is 21 ohms. So if you write out this, you will get a full point. That is 4 marks. So you can go over this again. What I encourage you to do is to close the solution and then pick up the questions on your own and solve them. So if you are able to arrive at the answers here, then you are good to go. So that is it. That's the solution for the problem. That's the solution for the problem, the tutorial problems at this time. So don't forget to like and share this video, and also subscribe to the channel if you haven't done so. So I see you in another video. Thank you. Bye-bye.